So if you look at what's on the docket for today, start off with nomenclature, then just talk about some basic bonding and geometry, refresh your minds a little bit. A little bit of overlap in Chem in that particular place. Go through some of the physical properties, relate intermolecular forces to things like melting point, boiling point, solubility. And then we'll do a hodgepodge of what I've just got labeled miscellaneous there on your sheet, which will really set us up for doing two very important things to finish off the night with. That's one, ranking acids and bases. And two, isomerism, in particular, the section we call in organic chemistry stereochemistry being the biggest part. So we'll end the night kind of on the two most important sections of the night and really just set them up with some background knowledge beforehand. So let's talk about nomenclature. So if you look on the right-hand side of your review sheet, just goes through, up through 12 carbons, what the prefix is: meth, eth, pro, bute, pent, hex, hept, oct, non-dec, undec, and dodec. So whether you need 11 and 12 is debatable, but you definitely need to know the first 10. It's usually the first 4 that give students the most problems. So like a pentagon is a 5-sided figure and students don't struggle there. A hexagon, 6-sided figure, no, students don't struggle there. Some of you guys might remember my little acronym for the first 4 is me, eat, peanut butter. So methyl, ethyl, propyl, butyl. So just get those straight in your head if it's indeed in the deep freeze. Let's look at some structures here. So let's look at a simple alkane to start with. So we'll start with the rules for naming alkanes and branch those out into some of the different functional groups and stuff like that. So what do we call it? 4-carbon alkane. Yeah, definitely just butane. So let's make this harder. So now I've put some substituents coming off here. So what's the first step? When you don't just have a simple straight chain, but you've got substituents, what's the first step? Find the longest carbon chain, first and foremost. What is my longest carbon chain here? 4. So 4 carbons. So how many different ways are there of getting 4 carbons? Multiples. So notice from this branch point here, whether I go to this methyl or this methyl or this methyl is arbitrary. And from this branch point over here, whether through this methyl or this methyl, same thing, it's arbitrary. So we'll just pick 4. So I'm going to go right across the middle because I like that. This looks nice. So, but second rule, which direction do I number it from? So not, what do you mean by greatest constituents, first of all?
The one that has the most on it.
What do you mean by has the most on it? So you want to number it in such a way that you come across the first substituent the earliest in the numerical system. So if I number it from left to right here, so we're going to make this our longest chain. If I number this from left to right, at what carbon do I come across my first substituent?
Second.
2, okay. If I would number it from right to left, where would I come across the first substituent?
2.
Also second, so it's a tie. So then we look, okay, if I go left to right, where would I come across the second substituent?
Second.
Also 2. If I go right to left, where would I come across the second substituent?
3.
3. So we're going to go left to right. We come across, we have a tie at substituent 1, so the second one we come across sooner. So we'll number it as such. How many substituents total we got on this thing?
3.
3. In this case, they're all what?
Methyl.
They're all methyl groups. So start off by naming the substituents. And how am I going to name these here? So give their location first. Where are these located?
2, 2, 3.
Good. 2, 2, 3. A lot of students forget that you got to say the number 2 twice. So if you're gonna, so what are we about to say here? Trimethyl. If you're going to say trimethyl, you better give 3 locations. So 2, 2, 3 trimethyl, and then what? Yeah, just butane. 4-carbon chain again. All one big, long, ugly word. So what is our goal in organic chemistry nomenclature? To make the longest word possible. So you'll see this time and again. So there is some rhyme to the reason here, some method to madness, but you'll see that oftentimes it just seems like we're trying to make the longest word possible. All right. Cool, so we got a cyclic alkane in this case. What's our cyclic alkane called? Cyclohexane. So how many substituents I got coming off my cyclohexane?
One.
Just one. So where does it have to be numbered?
One.
Yeah, has to be on number 1. So, and I can number it around either way. With it being the only substituent, it really doesn't matter if I go clockwise or anti-clockwise. So how am I going to name this? So you might think 1-ethyl cyclohexane, but with only one substituent on there, it has to be at number 1. It's a foregone conclusion. And so we actually don't include the 1 as part of the name. In fact, if you do put the 1 on there, it's wrong. So it's just ethyl cyclohexane in this case. So let's get a little tougher here. All right, so still got a cyclohexane. So first case, we now have a branched substituent. So what's the common name for this thing?
Isopropyl.
Yeah, he's an isopropyl group. What if I don't like common names? So this thing is, when you have a branched substituent, it's what we call a complex substituent. For some of the simpler ones, the 3 and 4 carbon variety, we have common names for them that are used much more commonly than the IUPAC complex substituent way. But what would I call this thing if I named it as a complex substituent?
1,1-dimethylmethane.
Not quite, not quite. But the carbon directly attached to the main chain automatically gets numbered carbon 1 if you name it as a complex substituent. And from there, you just move on and give it the longest chain possible. So whether I go 2 here or 2 here, same diff. And so this is looks like it should be a 1-methyl ethyl. But let me ask you a question. Could I have a 2-methyl ethyl? Is there any such thing as a 2-methyl ethyl? Well, if I put this methyl group on carbon 2 instead, what would I call it? I would have called it a propyl. So there's no such thing as a 2-methyl ethyl. So in fact, since the only type of methyl ethyl that exists is a 1-methyl ethyl, then we don't say 1 again, similar to what we did with the ethyl cyclohexane. In this case, it's just methyl ethyl. So whether we call it isopropyl or a methyl ethyl group, same diff. So what's our other substituent called?
Methyl.
Yeah, just a methyl in this case. Okay, so I got 2 substituents on my cyclohexane. How do I make sure I get the lowest possible numbers when I number this carbon chain? What's key in getting the lowest possible first number for a substituent location?
Start with 1.
Start with 1. So I start with 1 here, or I can start with 1 here, and either way I end up with a substituent at carbon 1. If I start with 1 here, where will I come across the second substituent?
3.
At 3. If I start with 1 here, where will I come across the second substituent? 3. So numerically, there's an absolute tie. So when you have a numerical tie, where it's the same exact numbers regardless of who you make number 1. So what breaks the tie? Alphabet. Alphabet, not largest, but alphabet. So it just goes alphabetical order, which means we got a problem, because, so do I call this a methyl ethyl or do I call it an isopropyl? Well, where it shows up in the alphabet changes depending on what you call it. Now I'm going to call it the most likely way you're ever going to see it, that's as an isopropyl group. So, but if I would call it a methyl ethyl, I'd alphabetize it under M. Well, methyl also gets alphabetized under M. What comes first in the alphabet, methyl ethyl or methyl? Just methyl. This one continues on. So who I decide to be number 1, in this case, depends on if I name it as the common substituent or the complex substituent. So in this case, though, I'm going to name it as an isopropyl. You'll hardly ever see anybody name this as a methyl ethyl. They'll call it isopropyl. And I does come in the alphabet before M. So my main chain here will go around the horn. So when you've got more than one substituent, in this case I should say more than one type of substituent. In this case we've got an isopropyl and a methyl. So when you name them, you name the substituents in what order? Alphabetical as well. Well, in this case, the numerical and the alphabetical match. That may not always be the case. This is one isopropyl, 3-methyl cyclohexane. Questions? Okay, let's make this a little harder. So I give you something like this instead. We're going to name it as a cyclohexane again. My question is, which carbon in cyclohexane gets to be carbon number 1? Why the one on the top?
It'll allow you to have the lowest number.
Good, it'll allow you to have the lowest numbers, especially after doing this last example we did. A lot of students see, oh, chloro is lowest in the alphabet. But when's the only time we ever go to the alphabet? There's an absolute tie in numerical designations. And here there's not going to be. I'm going to get the lowest possible number for the first substituent as 1, regardless of whether I go 1 here, 1 here, 1 here. So, but choosing him to be 1, my second substituent goes to 2, which I would have got as well if I made him 1 and him 2. But my third substituent is going to come down to 4, and that's where we're going to see the tie broken. So I never have to resort to the alphabet in this case. So there's one way that gives the lowest possible numbers for my substituents. Cool. So then we'll name our substituents. And again, which substituent do I name first?
Chloro.
Chloro. First in the alphabet. So the substituents, regardless of numbering, get named in alphabetical order. So there's 4-chloro. What's next?
Methyl.
Methyl. If you notice, hyphens separate letters from numbers all the time in naming. So 4-chloro, 1-ethyl, 2-methyl cyclohexane. Like I said, the goal is often to make as long a word as is humanly possible. So what's the first step? That's what I want you to think. So I want you to think, oh yeah, it's got an isopropyl. And it looks just like an isopropyl, except we're not going to name it as an isopropyl in this case. So one of the funky rules that kind of, every once in a blue moon you'll see it come into relevance is you find the longest carbon chain. And if there's more than one way to get the longest carbon chain, then you pick the one with the most substituents. So again, our goal is to make the longest word possible. So let's name as many substituents as we can. And so in this case, from this branch point here, I can go 2 carbons down this way, or 2 carbons over this way. But if I go this way, I'm going to get an extra substituent coming off as well. And so it's going to be coming down through here. And then numbered it across. So our longest chain is 6 carbons. Now, which way do I number it from? I number it from this end, where do I come across my first substituent? Not 1. 2. If I number it from this side, where do I come across my first substituent? Also from 2. In fact, I'm just going to circle my longest carbon chain here. If I number it from left to right, where do I come across my second substituent? 3. Right to left? Not till 4. So we'll number this left to right. All right, so we got 3 different substituents. 2 of them are methyls, the other one's an ethyl. We'll name them in alphabetical order, so the ethyl comes first. So 3-ethyl. Somebody help me out, what's next? 2-dimethyl. Hexane. Cool, so whereas hyphens separate letters from numbers, numbers are separated by commas. All right, let's look at some more complex functional groups. Kind of functional group I got right here.
Alkyne.
Cool. Use an alkyne. So you name alkenes or alkynes. Find the longest carbon chain that contains the alkene or the alkyne, and make sure that it gets the lowest possible number. So when we name an alkene or an alkyne, so notice it's not named as a substituent. It's actually named as part of the main chain. So my longest chain that contains the triple bond is what? 6. So we're going to call this hex, but instead of calling it hexane, we call it hexyne. So it's named as part of the main chain. So when a functional group is named as part of the main chain, it gets top priority. So I don't care if all of a sudden, I put a couple of methyl groups over here. I'd be like, Chad, make sure the substituents get the lowest possible numbers. And I'll be like, no. Make sure the major functional group that's named as part of the main chain gets the lowest possible numbers. I don't care about those at all. So in this case, we'll number it right to left. So in this case, I did add those 2 substituents, so we'll include this as part of the name. I've got 5,5-dimethyl. Hexyne.
Did you ever write hex 2y?
We're going there next. So the latest and greatest from IUPAC. So it says that you can, so when you're naming the location, when you're given the numerical designation of the location of a functional group that's part of the main chain, you can put the number right in the middle of the word and say hex 2-ine instead of 2-hexyne. So, because it just sounds really cool. You put a number in the middle of a word. It seems kind of stupid. It turns out when you have more than one major functional group that's included in the main chain's name, like if you had like an alkyne and an alcohol, we put both as part of the main chain, you'd have no choice but to put numbers in the middle of the word. But when there's just one major functional group, most people and most texts still to this day put them before the word because it just kind of looks stupid, putting a number in the middle of the word. But you may see some of this if you have more than one major functional group. It's not the most common question on a DAT or an MCAT. They usually stick with one major functional group. So you're not all that likely to see it, but don't be scared if you do see a number in the middle of the word. So the 2 tells me right where the ine is. Let's make this harder. here I'm going to give you one of those lovely molecules that has two major functional groups in it. With two major functional groups here, our first and foremost goal is not simply to find the longest chain. It is to find the longest chain that contains both functional groups, if possible. So, you know, we might have some long chain coming right off here that just keeps going, but it wouldn't be part of my longest chain here in this case because it wouldn't contain both major functional groups. So when you have multiple functional groups, your goal is to find the longest chain of carbons that contains both of them, not just the longest chain overall. So in this case, who gets the priority numbering? The alkene or the alkyne?
Alkyne.
So it turns out whichever one I can give the lower number wins.
Alkyne.
In this case, that would be the alkyne. If I continued this chain off a few carbons, then it would have been the alkene on the other side. So it kind of looks like they have equal priority, just whichever one you can give a lower number. So what if I do this? Now it's a tie, numerically. So the tiebreaker goes to the alkene. So just the way they designate it somewhere along the line. So with a tie, we'll number it to give the alkene the lower possible number. So our longest chain is 7 carbons. We have one constituent, a methyl of carbon 2. Where do I go from here?
Hept 2E59.
Good. So 2-methyl hept 2-ene 5-ine. So again, alkenes and alkynes get the lower of the two numbers involved. And in this case, with two major functional groups that are part of the main chain, I had to put the numbers in the middle of the word. No choice. You couldn't just say 2,5-heptenine. It doesn't work that way. Cool question.
So if you're going to do it the other way you had originally,
Without this methyl here,
right?
then I would have numbered it the other way.
Would that be 5-methyl hex 4-ene 1-ine?
So it would have indeed been 5-methyl hex 4-ene 1-ine. Cool, we'll talk later about alkenes. Whenever I see an alkene, I should think, ooh, does it have the possibility of having what? Cis-trans or EZ. In this case, does it have the possibility of having cis-trans or EZ? It doesn't, why not? And why do I recognize it so quickly?
Two of the groups are the same.
Two of the groups are the same. If either of the sp2 carbons is bonded to two identical substituents, and here this one's bonded to two identical methyl groups, then there is no EZ, there is no cis-trans, because they have equal priority, so you never get to give either of them a higher priority. There is no cis-trans in this case. So I chose this on purpose because we're going to deal with E and Z and cis and trans in another session. Okay, now I'll just bring to memory a whole host of functional groups. So somebody name for me a common functional group.
Alcohol.
Alcohol. We're just going to do a very simple alcohol. What is this alcohol right here?
Propanol.
It is propanol, but be more specific. 1 propanol. So you still got to give the location of where the OH is located. What kind of alcohol is this? Primary, secondary, or tertiary?
Primary.
It's primary. What determines it? What makes this thing primary? So we base it on where the carbon, where the OH is bonded. If you notice, how many bonds does oxygen typically make? 2. So for an alcohol, one of them is always to a hydrogen, and the other one is a carbon. So for an alcohol, the oxygen can only be bonded to one carbon as an alcohol. And so then it depends on the carbon. So it works that way with like alkyl halides and stuff as well. So, but let's look at amines for a sec. So what kind of amine is this?
Tertiary.
It's tertiary. What makes this a tertiary amine?
3 carbon.
3 carbons that are bonded to what?
The nitrogen.
To the nitrogen. So notice the difference in how we rank amines as compared to alcohols. Alcohols, their designation as primary, secondary, tertiary is based on the carbon bonded to the oxygen. But for amines, it's based on the nitrogen itself. And this nitrogen is bonded to 1, 2, 3 carbons. That's what makes it a tertiary amine. So note the difference. You may get a simple question, especially on the DAT, that just wants you to know the difference in how we designate alcohols versus amines. All right, so how are we going to name that? So find the longest carbon chain bonded to the nitrogen. How long is the longest carbon chain bonded to the nitrogen? I really want you to pick 3, but you shouldn't. It's 4. It's 4. So going right through here, now whether up or down, doesn't matter, but right through here is the longest chain. And we number it in such a way as to give the nitrogen bonded to the lowest numbered carbon. How many substituents do we have here? We got 3. Carbon 3, we have what? A methyl. But what else do we have? Methyls on the nitrogen as well, in the amine. So in this case, we know, yeah, 3-methyl, but a lot of students try and be like, oh, 2,2,3-methyl. But methyls aren't attached to carbon 2, they're attached to the nitrogen. And to designate their location, we just say they're attached to the nitrogen. So we say N dimethyl. In this case, we group all the methyls together, so we'll say 3N trimethyl. This is 3N trimethyl 2-butane. My functional group here, ketone. So ketones end with the suffix ONE. How do I name this ketone? So it's my longest chain containing the carbonyl carbon. 5. It is indeed 2-pentanone. It's my functional group here.
Aldehyde.
So for an aldehyde, the suffix we use to identify it is al. So what am I going to call this one? Butanol. Aldehydes are always anchored to the end of the chain. So if I'm naming something as an aldehyde, it has to be at carbon number 1. So I don't give its number. If it has to be number 1, no reason to give its number. So this is just butanol. Anybody recognize this functional group? It's an anhydride. In all likelihood, this is one of the less likely compounds or functional groups you'll have to name. Just kind of put it up here as a caveat, just in case, but it's not the most likely. So in this case, this anhydride is asymmetric. The carboxylic acid that was used to form the left-hand side is different than the carboxylic acid that would have been used to form the right-hand side. So in this case, you name each side. So 2 carbons on this side, 3 carbons on this side. So, and we name it from the carboxylic acids that were used to create it. So in this case, it was ethanoic acid or acetic acid, maybe either way, and then propanoic acid on this side. You name them in alphabetical order, so we'll say ethanoic, propanoic, anhydride. I think I need to hang up this green marker for a little while. What's my functional group here? Carboxylic acid.
Chat with the anhydride, but if they're symmetrical.
If it's symmetrical, good call. If it's symmetrical, like if this wasn't here, we would have just called it, instead of calling it ethanoic anhydride, which is still a proper name actually, it still works. Most people just shorten it down to just ethanoic anhydride. They just say it once. Good call. So, and we talked about how to name a carboxylic acid in naming the anhydride. So this one here, 3-carbon carboxylic acid. And again, carboxylic acid, they're just like the aldehyde, they're anchored to the end of the carbon chain, so they're always going to be located at position 1. And as a result, you don't give their number of where they're located. We just call this propanoic acid. One thing to note, and you'll see this show up rather commonly, especially on the DAT. So a common name, so for propanoic acid, it's just a slight variant of the name. This propionic acid, it's similar enough that most students figured out that it means the same thing. But just caveat. What's my functional group here? Ester. So in here, the major part of the ester is the side that contains the carbonyl carbon. The side that contains the carbonyl carbon. So let's do one more thing to this.
Carbonyl again means what?
Carbonyl is the, good question. Carbonyl is the carbon double bonded to oxygen. So in this case, that's the carbonyl carbon. So, and I meant to make this a benzene, FYI. So esters are based off the name of the carboxylic acid. So the carboxylic acid. So pretend this was an OH for a minute. If that were an OH, what would I call this thing? Benzoic acid. Benzoic acid. So if it were a deprotonated carboxylic acid, what do we call the conjugate base of a carboxylic acid in general? Called a carboxylate ion, a carboxylate ion. So in this case, without the H, this would be called the benzoate ion. The benzoate ion. And the ester is actually named off that carboxylate. So in this case, what's attached to the oxygen? Ethyl. You always name that first. So ethyl. So, and then you just name your carboxylate, whatever it might be. What's our carboxylate in this case again? Benzoate. So it's ethyl benzoate. So one thing to know, esters, a little more commonly tested than some of the others. You're definitely going to see alkanes and alkyl halides and things of the sort alkenes, alkynes. So when you start getting into these, like I said, the anhydrides you're not going to see too often. You'll see a carboxylic acid every once in a while, but students often remember those. So, but esters show up pretty routinely. So because they can really mess with the names, make a great multiple choice question. So let's do one more. Look at an amide. So amides are similar to amines. Amine, we learned the suffix is just amine for the main chain. Amides, same way. The suffix is just amide. So how do I name this thing? Yeah, these are anchored to the end of the chain too, just like carboxylic acids. We're just going to call this propanamide. And again, since it's anchored to the end of the chain, no reason to say one. And if you include the one, you say one propanamide, it's actually wrong. So don't include the one. Questions? So lots of functional groups. We went over alkanes early on with all the little nitty-gritty rules, and you definitely got to know those. And then just went over some very basic examples of these. Again, I could throw methyls and ethyls and propyls and isopropyls all over the place on these, if I so desired. Questions? Okay, one last thing. We're gonna have some fun. No, we're not gonna name this whole thing, FYI. I might be like, who wants to name this one? How do you say 19 carbons? So, but I just want to show you some of the complex substituents that you guys might see. So, if we look, what do we call that thing? As a substituent coming off the main chain, yeah, it's just a propyl group. So, the only isomer to propyl is the one we already learned. Since it's the only isomer of propyl, we just call it isopropyl. What do we call this guy?
Butyl.
Butyl. So when it comes to butyl, there's not just one isomer. There's quite a few. So we have like isobutyl and secbutyl and tertbutyl. So if we look, so when you've got a branched substituent, if the branch is right at the end, so it looks like it's ending in a fishtail, straight except for the very end, ends in a fishtail or a Y. So that's the isomer. So this is isobutyl in this case. So I could do isooctyl, and I'd have a 7-carbon chain with 1 fork right at the end as well. So you can do iso anything, but it's really the butyls that you'll probably ever see named this way. Okay, I'm going to put a straight 4-carbon chain here up top, but instead of bonding it through the end of the 4-carbon chain, I'm going to bond it through the middle of the 4-carbon chain. Before I attach it here, what kind of carbon is that right there? Primary, secondary, or tertiary? Before it's attached. It's secondary. So I'm attaching the butyl group to the secondary carbon. And so after I attach it, in this case it's tertiary, but it's named from what it looks like before it's attached. This is sec-butyl. And it's hyphenated, which is important. So, and what is this guy? Tertbutyl. Sometimes shortened down to T-butyl. Where do you suppose it gets its name? Looks like a T, but no. Turns out, that's how I remember it, but it turns out before it's attached, the carbon it's going to be attached through is a tertiary carbon. Hence the name tert-butyl. This isn't exactly an isomer of the butyl group because it actually has 2 less hydrogens, but what do I call this thing? That is, you know what, we're going to draw that over because that looks terrible. So what do we call this thing?
Cyclobutyl.
All right, so I put that up here for a reason. If you look, cyclobutyl and isobutyl and isopropyl, they're not hyphenated. And if you were to alphabetize these substituents, isopropyl and isobutyl get alphabetized under the letter I. And cyclobutyl gets alphabetized under the letter C. But when you look at sec-butyl and tert-butyl, which are hyphenated, they actually get alphabetized under the letter B, not T or S. So in case you're trying to figure out which order you name the substituents, you got to look at where they're being alphabetized by.
Which would come first of the two?
I honestly don't know which comes first out of 2, actually. So, and if I've never seen it in 10 years, then you're never going to see a molecule that's got one of each. But I honestly don't know. Cool, what do we call this guy?
Terpentyl.
So it's not a terpentyl. So, because it's not bonded to the tertiary carbon. So it is an isomer of a pentyl group. Turns out there's 8 of them, and you don't have to know them at all. They do have common names. There's neopentyl and isopentyl and tertpentyl. You don't got to know their names. You don't got to know what they look like. What you are expected to know is how to name it as a complex substituent. And again, as a complex substituent, the carbon attached to the main chain gets the first number. That's number 1, has to be. And then from there, you number it through to get the longest chain. So I'm just going to number it through like this. So this is a propyl group. At least it gets named as a propyl group. What's attached to my propyl group? 2 methyls. Where are they attached? Carbon 2 each. So we're going to call this a 2,2-dimethyl propyl group. So what kind of substituent is this again? It's complex. It has, it has a common name, but you get some bigger than this that don't even have common names. So the other ones here we looked at all had common names. He has a common name, but you don't got to know it. It's not something you're required to know. They do expect you to know how to name it as a complex substituent. So one thing to note, if you name this as part of a compound, complex substituents always go in parentheses, and they're alphabetized by the very first letter, even if it's part of the word di or tri. If you notice when we alphabetize like ethyl and methyl, we didn't worry about the dis and tris and tetras or anything like that. But as part of a complex substituents, whatever the first letter is, I don't care what it's part of, that's where you alphabetize it. Cool. That's nomenclature.